A star just exploded with the force of 1 billion suns. These are the universe's most energetic explosions, cosmic powerhouses that forge the elements of life and sculpt entire galaxies. In mere seconds, a single one can release more energy than every star in our Milky Way combined. We are about to journey through 25 mind-blowing facts about these celestial fireworks. You will discover the true scale of power that governs the cosmos. How can an explosion forge the gold in a wedding ring, and what cosmic event could pose a silent threat to our planet? What does the most violent death of a star reveal about our own beginnings? This single, blinding flash can briefly radiate more light than every other star in its home galaxy combined. That is the staggering reality of a supernova, the universe's ultimate power display. Think of our own sun, a steady furnace that has sustained life for billions of years. Now picture it releasing all of that energy, its entire lifetime output, in one single catastrophic second. That immense power is just a fraction of what a dying star unleashes. These explosions are not all the same, however. They come in different forms, each with its own cosmic trigger. One common type is the core collapse supernova. This happens when a truly massive star, many times heavier than our Sun, simply runs out of fuel. Its own immense gravity causes its core to collapse in on itself in less than a second, creating a violent rebound that blasts the star's outer layers into space. Another type, known as a Type Ia supernova, involves a stellar thief. A dense white dwarf star siphons material from a companion until it reaches a critical mass, triggering a runaway thermonuclear explosion so uniform that astronomers use them as cosmic mile markers to measure the vast distances of the universe. The aftermath of such violence is both beautiful and destructive. For years, the expanding cloud of stellar debris, a supernova remnant, glows with the energy of the explosion. A famous example is the Crab Nebula, a tangled web of gas and dust that is all that remains of a star witnessed exploding on Earth in the year 1054. This cosmic wreckage is more than just a ghost. It is a forge, scattering newly created elements across the cosmos, seeding space with the raw materials for everything we know. But for all their staggering power, even supernovae are not the final word in cosmic violence. That title belongs to gamma-ray bursts, the single most powerful explosion since the Big Bang itself. In just a few seconds, a single gamma-ray burst can unleash more energy than our Sun will produce across its entire 10 billion-year lifetime. These are not the long-lasting glows of a supernova remnant, but impossibly brilliant, ultra-short flashes of the highest energy light the universe can produce. For a fleeting moment, they outshine everything else in the cosmos combined. Astronomers divide them into two mysterious families. The long-duration bursts, lasting more than 2 seconds, are thought to be the final death cries of the most massive stars, collapsing not into a neutron star but directly into a black hole, sending a pair of ultra-focused jets screaming across space at nearly the speed of light. If one of those jets were pointed at Earth, we would witness the flash. The short-duration bursts, lasting less than 2 seconds, are even more extreme. They are believed to be the result of a catastrophic dance between two dead stars, neutron stars, locked in a final spiraling embrace before they collide and merge into a black hole. This event is so violent it shakes the very fabric of space-time, sending out ripples known as gravitational waves while also triggering that blinding flash of gamma rays. The greatest challenge in studying these cosmic beacons is their sheer unpredictability. They flash without warning from random points in the sky and are gone in an instant, leaving astronomers in a frantic race to capture their fading afterglow before it vanishes forever. What secrets about the birth of black holes and the creation of heavy elements are encoded in those fleeting signals? These jets are not a simple spherical blast, but cosmic blowtorches of pure energy. When the core of a massive star collapses directly into a black hole, It does not just explode outwards in all directions. Instead, immense magnetic fields and the rapid spin of the dying star focus the energy into two narrow beams, one erupting from each pole. These are the relativistic jets, and they move at over 99.9% the speed of light. They act like unimaginably powerful drills, punching their way straight through the outer layers of the star that are still collapsing inward. It is this violent escape, this focused beam of particles and radiation being squeezed through a stellar pinhole, that we observe as the intense flash of a long gamma-ray burst. Unlike the expanding sphere of a classic supernova, which spreads its energy in all directions, all the power of a gamma-ray burst is concentrated into these two narrow cones. This is why they appear so impossibly bright from Earth, but only if we are looking directly down the barrel of the jet. For every one we see, there are hundreds pointed away from us, completely invisible in the vast darkness. This extreme focus is the key to their terrifying power, a power that raises a chilling question. What would happen if such a jet from a star not too far away was aimed directly at our world? That same violent merger between two neutron stars that triggers a short gamma-ray burst also produces a second, distinct kind of explosion. This is the kilonova, a cosmic event of breathtaking consequence. While the gamma-ray burst is a focused flash, the kilonova is a brilliant, expanding cloud of stellar debris. Its true importance lies not in its raw power, but in what it creates. For within that hot, dense cloud, conditions are perfect for forging the universe's heaviest elements. Through a rapid process of neutron capture, atomic nuclei are bombarded and built up into substances far heavier than iron. This is the primary cosmic factory for gold, platinum, and even uranium. The event announces its productive work with a unique visual signature. Initially, the expanding cloud of debris glows with an intense, hot blue light. This is caused by the radioactive decay of lighter elements like silver and cadmium. But as the cloud expands and cools, the glow shifts to a deep, persistent red. This redder light comes from the decay of much heavier, newly minted elements, including lanthanides and that most sought-after metal, gold. A single kilonova event can forge an amount of gold weighing hundreds of times more than our entire planet. Every piece of gold jewelry, every platinum ring, contains atoms that were born in the fiery crucible of a neutron star collision, an explosion that happened billions of years ago, scattering these precious seeds across the galaxy. But to truly grasp the power behind a long gamma-ray burst, we need to look at the explosion that gives it birth. This is the hypernova, a supernova on cosmic steroids. While a typical core collapse supernova marks the death of a massive star, leaving behind a dense neutron star, a hypernova is something far more extreme. It is the final, catastrophic death scream of a star so massive and spinning so rapidly that its core does not just collapse, it completely and utterly fails. This special type of collapsing star is known as a collapsar. In a collapsar, the core's gravity is so overwhelming that not even the formation of a neutron star can halt the process. It continues to fall inward, directly forming a black hole. The star's rapid rotation is the critical ingredient here, whipping the infalling material into a superheated, spinning disk around the newborn black hole. It is from the poles of this system that the relativistic jets erupt, drilling their way out to create the gamma-ray burst we detect. The energy released in this single event can be up to 100 times greater than that of a standard supernova. A hypernova is not just a bigger bang, it is a fundamentally different kind of stellar death, one where a star's entire being is funneled into creating the most focused and powerful beams of energy in the known universe. That brilliant flash of gamma rays is just the beginning of the story. After the initial burst fades to black, a far more patient light show begins. This is the afterglow, a multi-wavelength echo that can linger for days, weeks, or even months. As the relativistic jets from the explosion plow into the surrounding gas and dust of interstellar space, they create a massive shock wave. This shock wave acts like a natural particle accelerator, causing the material to glow across the entire electromagnetic spectrum. It shines in X-rays, visible light, and radio waves, creating a slowly fading beacon that astronomers can track. This lingering glow is absolutely vital. The initial gamma-ray burst is so brief and its position so poorly defined that without the afterglow, we would often have no idea where in the vast cosmos it came from. The afterglow acts as a detailed cosmic address, allowing telescopes to swivel toward the source and pinpoint the burst's exact host galaxy, sometimes billions of light years away. But the afterglow does more than just provide a location. By carefully monitoring how its light fades over time across different colors, scientists can perform a kind of cosmic forensics. The specific rate at which the X-ray, optical, and radio emissions dim reveals the total energy that was pumped into the shock wave. It also tells us about the geometry of the explosion itself, confirming whether the energy was indeed focused into a narrow jet, like a cosmic spotlight, or spread more widely. Each observation of a fading afterglow is a race against time, a desperate effort to decode the final message of a cataclysm that reshaped a tiny corner of the universe. This concentrated power raises a chilling possibility. What if a gamma-ray burst happened in our cosmic backyard within just a few thousand light years of Earth, and its deadly jet was aimed directly at us? The consequences would be far more insidious than a simple bright flash in the sky. The real danger lies in the aftermath. That focused beam of gamma radiation would deliver a catastrophic blow to our planet's atmosphere. It would rip apart nitrogen and oxygen molecules, triggering a chain of chemical reactions that would utterly destroy the ozone layer, our planet's vital shield against the sun's harsh ultraviolet rays. With that protective blanket gone, the surface would be bathed in lethal levels of UV radiation. This would not be an instant fireball, but a slow-moving ecological collapse. The base of the food chain, phytoplankton in the oceans, would die off, crops would fail, and any life exposed to the sun would suffer severe genetic damage, potentially leading to a mass extinction event on a global scale. Yet before this unsettling thought takes root, it is crucial to understand just how unlikely such a scenario truly is. For a gamma-ray burst to pose a threat, two very specific conditions must be met simultaneously. The burst must occur relatively close by in galactic terms, and its incredibly narrow jet must be pointed with perfect precision at our solar system. Given the vast number of stars and the random directions of these jets, the odds of Earth finding itself in the crosshairs are astronomically low. There are no candidate stars within the danger zone that are poised for such an explosion. So while the physics of the threat are real, we can rest assured that our planet is safe from this particular cosmic catastrophe. The reassuring safety of our galactic neighborhood was spectacularly demonstrated in February 1987. That is when a star in the Large Magellanic Cloud, a satellite galaxy of our own Milky Way, reached the end of its life. Designated Supernova 1987A, it was the closest and brightest supernova witnessed in nearly 4 centuries, visible to the naked eye in the southern hemisphere. For astronomers, it was not just a light in the sky, it was a once-in-a-lifetime opportunity, a stellar death happening practically in our own cosmic backyard. The event began not with visible light, but with an invisible whisper from the heart of the explosion. Just hours before the light from the blast reached Earth, underground detectors in Japan and the United States recorded a tiny, fleeting pulse of 24 neutrinos. These nearly massless ghost particles, produced in staggering numbers during the core collapse, had streamed straight out of the dying star, unimpeded by the overlying stellar material, while the visible shockwave was still fighting its way to the surface. This was the first and only time neutrinos from a supernova have ever been detected, and it provided direct, tangible proof of the core collapse mechanism that theorists had long proposed. The story did not end with that initial flash. In the years that followed, the Hubble Space Telescope revealed an astonishing structure around the remnant. It was surrounded by a magnificent glowing hourglass of gas with 3 distinct rings. The central ring, a loop of material ejected by the star thousands of years before its death, began to light up as the supernova's ultraviolet flash struck it, illuminating a pre-existing fossil from the star's final chapter. Watching this ring brighten and then fade has given us a front-row seat to the aftermath of a supernova, teaching us how the ejected debris interacts with its ancient surroundings. Decades later, we continue to study this cosmic laboratory. We have watched as the expanding shockwave collides with the inner ring, heating it to millions of degrees and triggering the formation of new, incredibly hot blobs of gas. Supernova 1987 is the gift that keeps on giving, a detailed case study that continues to refine our understanding of how massive stars live, die, and ultimately enrich the cosmos. For stars of truly monstrous size, death is not a collapse but a complete and total annihilation. We are talking about stars so immense they dwarf even the hypernova progenitors, stars that push the very limits of what is physically possible. These cosmic leviathans, with masses between 130 and 250 times that of our Sun, face a fate so utterly destructive that it erases them from existence. The mechanism is known as a pair instability supernova, and it begins deep within the star's own heart. Under normal conditions, the intense heat and pressure in a stellar core create gamma-ray photons. These photons push outward, providing the pressure that holds the star up against its own crushing gravity. But in these supermassive stars, the core becomes so phenomenally hot and dense that the gamma rays themselves begin to behave strangely. They spontaneously transform, converting their pure energy into matter and antimatter pairs, specifically electrons and their antimatter counterparts, positrons. This transformation is catastrophic. Those gamma rays were the main source of the core's internal pressure. By turning into particles, that supporting pressure suddenly vanishes. It is as if the foundation of a skyscraper instantly turned to dust. With no outward force to resist it, the star's own immense gravity triggers a sudden, violent collapse. This is not the gentle fading of a campfire, but the entire structure giving way at once. The collapse does not last long, however. The inrushing material heats the core to unimaginable temperatures, sparking a runaway thermonuclear explosion far more powerful than any standard supernova. The entire star, from its core to its outermost layers, is utterly and completely torn apart in a blast of pure fusion fire. There is no remnant, no neutron star, no black hole. The star simply ceases to be, scattering its enriched guts across space without a single trace of its former self. This ultimate self-destruction ensures that the universe's very largest stars leave no corpse behind, vanishing in a final, dazzling act of cosmic suicide. Even the dead husks of stars can harbor unimaginable violence. After a supernova's fury subsides, the collapsed core left behind is often a neutron star, a city-sized object so dense a single teaspoon of it would weigh billions of tons. Most are relatively quiet, but a rare few become something far more terrifying, a magnetar. These are neutron stars born spinning furiously and possessing magnetic fields so powerful they defy comprehension. A magnetar's magnetic field is 1,000 trillion times stronger than Earth's. If one were located halfway between Earth and the Moon, its magnetic pull would effortlessly erase the data from every credit card on our planet. This unimaginable stress constantly strains the magnetar's rigid crust, a solid surface of iron-like material under immense pressure. Eventually, the crust can no longer contain the pent-up energy, and it fractures in a starquake, an event that makes our most powerful earthquakes seem like a gentle tremor. This catastrophic rupture unleashes a giant flare, an outburst of radiation so intense it can, for a fraction of a second, outshine every other source of gamma rays in the entire sky. On December 27, 2004, a giant flare from a magnetar 50,000 light-years away temporarily compressed our planet's upper atmosphere, its powerful waves of energy actually distorting Earth's magnetic field from afar. While these magnetic explosions are less energetic than a full gamma-ray burst, they represent an entirely different class of cosmic cataclysm, a stark reminder that even in stellar corpses, magnetic fury can erupt without warning. While the visible explosion of a supernova is blinding, its true power is channeled through an invisible tide. In the very first moments of a core collapse supernova, a staggering 99% of the star's gravitational energy is not released as light, but is instead carried away by a ghostly exodus of neutrinos. These subatomic particles are so tiny and elusive that they can pass through light years of lead without a single interaction. In that final, catastrophic collapse, the core of the star becomes so dense that it traps even light itself, but neutrinos simply stream outward, a silent herald of the violence within. This means that for a brief, incredible moment, the dying star shines 1,000,000 times brighter in neutrinos than it does in every other form of energy combined. The detection of just 24 of these particles from supernova 1987 was a monumental achievement. It was not merely a confirmation, it was our first and only direct telegram from the heart of a collapsing stellar core, received hours before the light from the blast even reached us. This neutrino pulse provided undeniable proof of the core collapse model, a fleeting glimpse into the central engine of stellar death. By studying these faint whispers, physicists can peer directly into conditions that are otherwise forever hidden, decoding the very first seconds of a cataclysm that will later paint the sky with light. Deep within the chaos of a stellar explosion, a hidden music begins. The newborn proto-neutron star, a city-sized sphere of unimaginably dense matter, does not form in perfect silence. It rings, violent turbulence and the intense heating from that flood of escaping neutrinos set its entire structure oscillating, sending powerful sound waves reverberating through its hyper-dense interior. These are not sounds as we know them, of course, for sound cannot travel through the vacuum of space. This is a symphony of pressure waves, a deep, resonant hum on a scale we can barely comprehend. The frequencies of these oscillations are far too low for the human ear, but if we could hear them, they would resemble the deep, resonant tolling of a cosmic bell. These internal vibrations are far from just a curious side effect. They may play a crucial role in the supernova explosion itself. The specific patterns of these ringing waves can help push the stalled shockwave outward, reigniting the blast and helping to finally blow the star apart. This internal music might even influence the final chemical composition of the expanding debris cloud. The way the star rings determines how the shockwave travels through its different layers, affecting which heavy elements are forged in the fire and how much of each is ultimately scattered into space. The death of a star is not just a visual spectacle, but a complex physical event with its own unique sonic signature, a deep vibration that helps sculpt the very elements that will one day form new worlds. The silent rain of cosmic rays is a constant, unseen presence all around you. These are not rays of light, but atomic fragments, protons and atomic nuclei hurtling through space at nearly the speed of light. For over a century, their origin was one of astronomy's greatest puzzles. Where does the universe find the power to launch such energetic particles? The answer lies in the expanding fireballs of supernova remnants. The colossal shockwave from the explosion acts as a perfect natural particle accelerator, far more powerful than anything we could ever build on Earth. As this spherical wall of energy and debris plows through interstellar space, it sweeps up stray protons and atomic nuclei. Magnetic fields within the shockwave trap these particles, forcing them to bounce back and forth across the turbulent front. With each crossing, they gain a tremendous burst of speed, like a surfer being pushed repeatedly by an endless wave. After thousands of these cycles, the particles are eventually flung out into the galaxy. Ejected with so much energy, they become the cosmic rays that constantly bombard our atmosphere. We now have direct proof of this process. Telescopes designed to see the highest energy light observe a diffuse glow of gamma rays emanating from several known supernova remnants. This glow is the telltale signature of cosmic ray production, created when those accelerated particles smash into slower-moving gas, a brilliant confirmation that these stellar wreckages are the universe's ultimate particle accelerators, operating on a scale we can only stand in awe of. These first stars were cosmic titans born from a universe of only hydrogen and helium. Without any heavier elements to help them cool and fragment, they grew to staggering sizes, some containing the mass of several hundred suns. Their pristine composition meant their internal engines burned at ferocious temperatures, leading to incredibly short, violent lives. When these population 3 stars finally reached their end, their deaths were cataclysmic events unlike any we see today. For the very largest among them, their fate was a pair instability supernova, a blast of pure fusion fire so complete it left no remnant behind, scattering the first heavy elements into the void. Other massive first stars may have bypassed an explosion entirely. Their immense gravity could have caused a direct collapse, the entire star simply winking out of existence to form a black hole without the brilliant fireworks of a supernova. These contrasting deaths set the stage for everything that followed. The pair instability explosions seeded the early cosmos with its first metals, the crucial building blocks for rocky planets and ultimately life. The silent direct collapses, however, left behind the seeds of the supermassive black holes that now anchor the centers of galaxies. The violent end of these first stars was the universe's first act of true creation, forging the raw materials and the gravitational anchors from which all future cosmic structures would one day arise. The death of a star is not always an internal collapse. Sometimes it is a violent abduction. Far from the stellar nurseries where stars are born, in the silent, dark hearts of galaxies lurk supermassive black holes. When an unlucky star wanders too close to one of these gravitational monsters, it experiences a fate that defies imagination. The black hole's immense tidal forces, the difference in gravity between the side of the star nearest the hole and the side farthest away, become overwhelming. This gravity gradient pulls so fiercely that it overcomes the star's own gravity, the very force that has held it together for millions or billions of years. The star is not simply swallowed whole, it is stretched and compressed, shredded into a long, thin stream of incandescent gas in a process aptly named spaghettification. This is a tidal disruption event. The resulting stream of stellar debris does not vanish. About half of it is flung out into the void, while the other half falls back toward the black hole, swirling into a superheated, glowing disk of accretion. As this material spirals inward, it is heated to temperatures of millions of degrees, producing an intense flare of radiation that can outshine every star in its host galaxy for months. This brilliant flash is a beacon pointing directly to a previously dormant black hole, one that was sitting quietly in the dark, invisible to our telescopes. By studying the light from these flares, astronomers can probe the physics of matter in the most extreme gravitational environments, watching how a black hole feeds and learning the secrets of accretion, the final journey of matter before it crosses the point of no return. Just when we thought we had categorized the universe's most violent explosions, it surprised us with a new mystery. In June 2018, a survey telescope spotted something bizarre, an event so peculiar it was quickly nicknamed the Cow. It appeared in a galaxy 200 million light-years away, flaring to incredible brightness and then fading with shocking speed. This was no ordinary supernova. It was something entirely new, a luminous fast blue optical transient. The name itself describes its strange nature. These events are intensely luminous, far brighter than a typical supernova for a brief moment. They shine with an unusually blue light, indicating extremely high temperatures, and their optical light fades away in just days, not the weeks or months of a classic supernova. The Cow reached its peak brightness in under 2 days and was mostly gone in a month, a fleeting cosmic firework that left astronomers scrambling for explanations. What kind of explosion could be this bright, this hot, and fade this fast? The leading theories are as dramatic as the event itself. One compelling idea is that we are witnessing a failed supernova. In this scenario, a massive star collapses, but its outer layers do not get successfully blasted away in a grand explosion. Instead, the collapse forms a black hole directly at the star's core, which then begins to voraciously feed on the infalling stellar material. This creates a swirling accretion disk of superheated debris, and from the poles of this newborn black hole, narrow jets of material erupt at near light speed. If we happen to be looking directly down the barrel of one of these jets, we would see an incredibly bright, rapidly fading flash of blue light, exactly matching the properties of the Cow. Another possibility points to a stellar merger of an exotic kind, perhaps between a white dwarf and a neutron star, or even 2 neutron stars, resulting in a brief, intensely hot fireball. The existence of luminous fast blue optical transients proves that our map of stellar death is far from complete. Each new detection, each new Cow-like event, forces us to reconsider our models and reminds us that the universe holds violent phenomena we are only just beginning to name. Sometimes a star's cry for help can be mistaken for its final scream. In the 1840s, the massive star system Eta Carinae in our own galaxy erupted, violently expelling huge amounts of its own mass and briefly becoming the second brightest star in the entire night sky. To observers of the time, it looked for all the world like a supernova, a star meeting its end. Yet Eta Carinae did not die. It survived this colossal outburst, and the event was not a true supernova at all, but a supernova imposter. This is the critical difference between a terminal explosion and a giant eruption. A true supernova is the final, catastrophic death of a star, an irreversible destruction of its core. A supernova imposter, however, is a stellar tantrum of epic proportions, a temporary instability that causes the star to blow off its outer layers in a massive belch of gas and dust, while the star itself continues to shine, wounded but still very much alive. The evidence of Eta Carinae's great eruption now surrounds it in the form of the magnificent Homunculus Nebula. This beautiful, hourglass-shaped cloud of glowing gas is not a supernova remnant, but a fossil of that 19th century outburst, a three-dimensional map of the material the star ejected. The star itself remains at the nebula's heart, a volatile and unpredictable titan that could still explode as a genuine supernova at any moment, perhaps within the next several thousand years. These imposter events are a stark reminder that the universe often blurs the lines between a near-death experience and the real thing, forcing us to look more closely at every brilliant flash in the night. That precise 1.4 solar mass limit is a fundamental line in the sand for the universe. It is known as the Chandrasekhar limit, named for the astrophysicist who first calculated this critical threshold. This is the maximum mass a white dwarf star, the dense Earth-sized core left behind by a Sun-like star, can possibly support. A white dwarf is a bizarre object, a sphere of carbon and oxygen so compressed that it is held up not by fire, but by a quantum mechanical effect known as electron degeneracy pressure. The electrons inside it are packed together as tightly as the laws of physics will allow, and they push back fiercely against the star's own gravity. But this support has a strict upper limit. If the white dwarf is in a binary system, it can act as a gravitational thief, slowly siphoning hydrogen and helium from its companion star. This stolen material builds up on the white dwarf's surface, increasing its mass. As the scale tips closer and closer to 1.4 times the mass of our Sun, the pressure in its core becomes unbearable. The electrons can no longer hold back the collapse. In a single runaway instant, the entire core ignites. The carbon, which was formerly inert, suddenly fuses into heavier elements like nickel and iron. This is not a gentle burning, but a full-scale thermonuclear detonation that rips the entire white dwarf apart from the inside out. There is no remnant, no neutron star. The star is completely vaporized in a flash of light that can outshine an entire galaxy. This utter destruction is what makes these type Ia supernovas so valuable to astronomers. Because the explosion always happens at the exact same mass threshold, the physics of the detonation is nearly identical every single time. This means their peak intrinsic brightness is always virtually the same. When we observe one in a distant galaxy, we know its true luminosity. By measuring how dim it appears from Earth, we can calculate with incredible precision just how far away that galaxy is. These stellar bombs become cosmic mile markers, the gold standard for measuring the vast expanses of the universe and the rate of its expansion. Every atom of gold in a wedding ring or a treasured heirloom carries a violent cosmic history. These heavy elements, everything from the silver in photographic film to the uranium that powers reactors, cannot be forged in the calm furnaces of ordinary stars. Their creation requires a far more extreme environment, a storm of subatomic particles so intense it can only occur during the universe's most energetic explosions. This process is called the rapid neutron capture process, or the R process for short, and it is the primary cosmic mechanism for building elements heavier than iron. Imagine an atomic nucleus caught in a torrent of free neutrons. Under the incredible temperatures and densities of a supernova's inner shockwave or the debris cloud of colliding neutron stars, neutrons bombard the nucleus faster than it can naturally decay. It is like trying to build a snowball in a raging blizzard, with new snow sticking to it faster than the old snow can melt. The nucleus rapidly grows heavier and heavier, bloating with neutrons until it becomes unstable. At that critical point, some of those neutrons transform into protons through radioactive decay, effectively creating a new, heavier element. This frantic sequence, repeated billions of times in a matter of seconds, forges the entire upper half of the periodic table. A supernova can seed space with these new elements, but the true heavy element factories are the Kilonovae born from neutron star mergers. In that hot, dense cloud of stellar debris, conditions are perfect for an overwhelming R process event, creating vast quantities of gold, platinum, and other rare earth elements. This means the precious metals we value so highly on Earth are in fact the scattered ashes of ancient stellar cataclysms. We are not just living in a universe of stars, we are literally made from the remnants of their most spectacular deaths. That precise 1.4 solar mass limit did more than just create cosmic mile markers. It unveiled a secret the universe had been hiding. In the late 1990s, two independent teams of astronomers were using these perfect standard candles, the type Ia supernova, to measure cosmic distances with unprecedented accuracy. Their goal was to determine the rate at which the universe's expansion was slowing down, pulled back by the collective gravity of all the matter within it. They meticulously compared the observed brightness of these supernovae in distant galaxies to their redshift, which is the stretching of light waves caused by the expansion of space itself. A greater redshift means the galaxy is moving away faster and the light has traveled a longer distance to reach us. What they found was not a slowdown but a shock. The most distant supernova, the ones whose light had been traveling for billions of years, were significantly dimmer than their redshifts predicted. This meant they were farther away than anyone had calculated. The only possible explanation was that the expansion of the universe was not slowing at all. It was speeding up. This was a discovery so profound it overturned the fundamental narrative of cosmology. Some unknown repulsive force, now called dark energy, was acting against gravity, pushing galaxies apart at an ever-increasing rate. This revelation earned the leaders of the teams the Nobel Prize in Physics in 2011, and it completely reshaped our understanding of the cosmos's ultimate fate. The universe is not just expanding, it is accelerating into a future of increasing isolation and darkness, all revealed by the self-destructive flash of a dying white dwarf star. This new era of cosmic discovery is being powered by a revolutionary eye in the sky. The James Webb Space Telescope, with its golden mirror and infrared vision, is peeling back layers of time and dust to reveal the secrets of stellar explosions in ways we never thought possible. While Hubble gave us breathtaking portraits of supernova remnants, Webb sees straight through the obscuring cosmic dust to analyze the chemical fingerprints within. Its powerful spectrographs dissect the faint light from these distant fireballs, identifying the specific elements forged in the blast with a precision that is like moving from a blurry photograph to a detailed laboratory analysis. This allows us to read the story of a star's death written in the elemental makeup of its debris, confirming for the first time the precise yields of heavy elements like carbon, oxygen, and iron scattered into the void. But Webb's most profound power is its ability to function as a true time machine. By staring deep into the cosmos, it collects light that has been traveling for over 13 billion years, allowing it to witness the very first generations of supernova. These were the explosions of the primordial population 3 stars, the ones that first seeded the barren early universe with the heavy elements necessary for life. We are no longer just theorizing about these foundational events. We are now beginning to capture their direct, fading light, watching the universe's first great acts of creation and destruction as they happened. This is more than just better imagery. It is a fundamental shift in our understanding, allowing us to trace the complete cosmic cycle of death and rebirth from the first star to the elements that make up our own world. A single flash of light is no longer our only window into these cataclysms. We have entered a new age of discovery, an era of multi-messenger astronomy, where we perceive the universe not just with our eyes, but with entirely new senses. This approach combines the traditional study of light with the detection of gravitational waves, the ripples in spacetime itself, and the ghostly stream of neutrinos. The power of this new perspective was proven beyond doubt on August 17, 2017. On that day, gravitational wave observatories detected a signal not from colliding black holes, but from a pair of orbiting neutron stars spiraling inward. For the first time ever, we had heard the death spiral of these incredible objects. Just 2 seconds later, orbiting telescopes spotted a short gamma ray burst originating from the exact same patch of sky. The hunt was on. Telescopes across the globe and in space swiveled to that point, and within hours they found it, a brand new point of light in a galaxy called NGC 4993. This was the Kilonovae, the visible fireball from the merger, and it was glowing with the telltale signature of newly forged heavy elements. This single event, designated GW 170817, was a scientific bonanza. By combining the gravitational wave signal with the light from the Kilonovae, astronomers could confirm once and for all that neutron star collisions are indeed the primary cosmic factories for elements like gold and platinum. The gravitational waves told us the masses of the objects and the nature of their violent dance, while the light revealed the chemical composition of the material they blasted into space. But the discoveries did not stop there. This single event also provided a completely independent way to measure the expansion of the universe. The gravitational waves gave us a direct measure of the distance to the source, while the redshift of the host galaxy gave us its speed of recession. By comparing these two values, scientists could calculate the Hubble constant, the rate of cosmic expansion, with a precision that helps resolve one of the biggest ongoing debates in cosmology. One collision, observed through multiple cosmic messengers, answered fundamental questions that had puzzled us for decades. Our own sun, the steady star that gives us life, will never experience such a violent end. It is simply too small. A star needs to be at least 8 times more massive than the Sun to muster the gravitational fury required for a core collapse supernova. Instead, our Sun's final act will be a far more gentle and beautiful transformation. Billions of years from now, after it has exhausted the hydrogen fuel in its core, it will swell into a magnificent red giant, its outer layers expanding to engulf the inner planets. But this inflated state is temporary. Its core will contract into an incredibly dense, Earth-sized ember known as a white dwarf, while the star's outer atmosphere is gently pushed away into space by the pressure of its own remaining light. This expanding shell of glowing gas will form a planetary nebula, a luminous and often intricate cosmic bubble that will glow for tens of thousands of years before gradually fading into the darkness. At the heart of this nebula, the white dwarf will remain, a fading diamond of carbon and oxygen that will slowly cool over trillions of years. This peaceful demise stands in stark contrast to the hypernova and gamma-ray bursts that tear massive stars apart. The Sun's quiet end is the rule, not the exception, for the vast majority of stars in our galaxy. Its stable, predictable life cycle is what allowed our planet to form and life to flourish, a testament to the fact that sometimes the most important cosmic stories are not written in fire and fury, but in patient, enduring light. To truly understand a supernova, we must attempt to recreate its heart on Earth, a task that pushes the very limits of modern computation. These explosions are far too complex for simple equations or two-dimensional models, involving a chaotic dance of gravity, nuclear physics, and subatomic particles all unfolding in a fraction of a second. Scientists therefore turn to some of the world's most powerful supercomputers, machines capable of performing quadrillions of calculations per second, to build a virtual star and watch it die. The challenge is immense, requiring a three-dimensional simulation that tracks the collapse of the iron core, the behavior of the shockwave as it stalls and must be revived, and the intricate transport of trillions upon trillions of neutrinos as they flee the carnage. Adding the intense, twisted magnetic fields that can birth relativistic jets increases the difficulty exponentially, creating a puzzle of almost unimaginable scale. These digital laboratories are not just for show, they are essential bridges connecting our theoretical predictions to the actual light and neutrinos we observe from real stellar deaths. Often, the simulations reveal surprises that pure theory never anticipated, like how the turbulent churning of matter and the deep, resonant ringing of the newborn neutron star can help push the shockwave outward, turning a fizzling collapse into a successful, galaxy-shaking explosion. Each simulation is a voyage into the unknown, a digital dissection of a cosmic catastrophe that shows us just how much we still have to learn from the violent end of a star. Our growing understanding of cosmic explosions is about to leap forward with a new generation of observatories. The Vera C. Rubin Observatory, poised to begin its monumental survey of the sky, will not look at the universe as a static picture, but as a dynamic, ever-changing movie. Its enormous camera will scan the entire visible sky every few nights, not just once, but over and over for a decade. This relentless watch will catch the fleeting births and deaths of stellar cataclysms as they happen, discovering not dozens but thousands of new supernova, gamma-ray bursts, and other brilliant transients every single year. It will find them earlier and fainter than ever before, giving us a front-row seat to the very first moments of an explosion. This flood of new data will transform our view from studying rare, individual events to understanding the entire life cycle of stellar death across cosmic time. At the same time, a completely different kind of observatory will be listening to the cosmos. The LISA mission, a space-based gravitational wave detector, will open an entirely new sense. Unlike ground-based observatories that hear the high-pitched chirps of stellar mass black holes, LISA is designed to sense the low-frequency rumble of the universe's most massive events. It will detect the gravitational waves produced when supermassive black holes, millions or even billions of times the mass of our Sun, collide and merge in the hearts of distant galaxies. This will be the sound of the largest explosions since the Big Bang itself, events that shake the fabric of space-time on a scale we can barely conceive. Together, these new eyes and ears on the cosmos will paint a more complete picture than ever before, revealing the full symphony of the universe's most energetic explosions, from the first flash of light to the deep, resonant tremors in the fabric of reality. From the silent collapse of a stellar core to the brilliant flash of a gamma-ray burst, these cosmic explosions represent the full spectrum of power in our universe. We have journeyed from the supernova remnants that seed galaxies with life-giving elements to the Kilonovae that forge the gold in our jewelry. We have witnessed the magnetic fury of magnetars and the silent whispers of neutrinos that herald a star's death. Each cataclysm, from a colliding neutron star to a star being shredded by a black hole, plays a vital role in the great cosmic cycle. These events are not merely destructive forces, they are the universe's most essential creators. They forged the iron in your blood, the calcium in your bones, and the oxygen you breathe. They sculpt the evolution of galaxies and measure the expansion of space itself. The next time you gaze up at the night sky, remember that you're looking at a universe alive with both fire and creation. Let us know which of these 25 facts reshaped your view of the cosmos. Share your favorite discovery in the comments below.